An 828-meter skyscraper is a multi-billion-dollar physics problem. Every vertical meter is solved equation by equation through years of predictive modeling. The design is a struggle between opposing forces. Gravity pulls millions of tons straight down, while lateral wind shear pushes horizontally. Typically, gravity is the primary concern, but approaching 1 kilometer, dynamic lateral wind force overtakes dead load as the absolute limit on survival. Pushing beyond the 800-meter mark requires abandoning traditional rectangular footprints. To survive, engineers must utilize algorithmic massing and aerodynamic manipulation, requiring thousands of variables to be solved through calculus. Building at this scale is a constant negotiation between structural limits and the laws of physics. Consider a horizontal beam bearing a downward load. The top experiences compressive stress, the bottom tensile. The formula M max equals WL squared over 12 proves length and load dictate central stress. Rotated vertically, it's a skyscraper resisting horizontal wind, enduring identical extreme stresses. Scaling a standard square footprint to 1 kilometer introduces a severe structural flaw. Resisting that immense bending moment would require walls so thick they would consume the building's interior, leaving no room for the people inside. This floor plan shows the Burj Dubai's Y-shaped cross-section, the solution to managing bending moments. At the center is a hexagonal hub providing resistance against torsion. Radiating from that hub are 3 wings catching shear and moment forces. Each wing buttresses the central core. If the wind pushes against one wing, the other 2 stand rigid. Because the central core and column elements align perfectly, the load travels straight to the foundation without requiring heavy structural transfers. This geometry lets the tower manage extreme stresses using only optimally placed, high-performance concrete vertical elements. Managing the internal load is only half the problem. Architects must also contend with external fluid dynamics, specifically how high-altitude winds interact with solid surfaces. When wind hits a flat-faced building, it doesn't just flow around it. It creates alternating, swirling low-pressure zones in its wake. This is vortex shedding, and it pulls the structure from side to side. Every building has a natural frequency, a specific rhythm at which it naturally wants to sway. This graph illustrates dynamic resonance. If alternating vortex shedding matches the building's natural frequency, side sway amplifies until movement becomes catastrophic. A 1-kilometer tower cannot be built stiff enough to resist resonance through mass alone. To stay standing, the design must proactively disrupt the behavior of the wind itself. By running scale models through boundary layer wind tunnels, engineers developed an aerodynamic solution, spiraling asymmetrical setbacks. As the tower rises, the wings step back in a clockwise sequence. These setbacks alter the building's width and footprint at every level. This design is intended to confuse the wind. Because the building's profile is constantly changing, wind vortices never encounter a uniform surface long enough to organize or build a dangerous rhythmic frequency. This chart maps the across-wind modal force. The sharp peak represents a basic tower succumbing to resonance. The flattened curve shows the Burj Dubai's step design, proving the vortices have been successfully disorganized. The spiraling profile is an engineered mechanism designed to neutralize across-wind forces and defeat resonant dynamics. Beyond geometry and fluid dynamics, engineers must account for the 4th dimension, time. High-performance concrete is durable, but it deforms under immense dead load over a multi-year horizon. Millions of tons of gravity cause microscopic compression known as creep and shrinkage. Across 160 floors, these tiny changes compound into structural shifts. Engineers run time-dependent analyses to predict how the tower drifts as concrete settles. Models predicted a 200-millimeter side sway over 10 years. To correct this, crews recentered the core wall at each level, building a lean that gravity will eventually pull straight. Building at this scale requires solving the physics of material deformation years before it actually occurs. Millions of calculations were required before a single friction pile was driven into the bedrock. Every aspect of the tower's survival was simulated a decade into its future. The final structure is a unified solution. The buttressed core manages the static vertical load, while the spiraling setbacks neutralize the dynamic aerodynamic forces from the wind. Today, these simulations exist as digital twins, virtual models that continuously calculate how a structure responds to its environment. They are now the mandatory proving grounds for all modern megaprojects. Advanced calculus is the tool for algorithmic optimization. It allows engineers to minimize material waste while maximizing the structural and economic capacity of the building. Steel and concrete form the physical shell of these structures, but it is the precision of the underlying mathematics that allows them to stand. Our tallest cities are the soaring reality of perfect equations.